So in this video, we will be deriving the time dilation formula. Before we proceed to the specification of this formula, the first thing that I need to do is let me first show you the actual formula of this time dilation. So we have the change of time is equal to the change of time, stationary time, over the square root of 1 minus v square and c square. So this is the very basic formula for our time dilation. Now the question is how this is being derived to this. How did they come up with this particular formula? So in this case, we need to consider two things. The first thing is these are actually setups. In our illustration, I'll be showing to you the setup 1 and the setup 2. In setup 1, it is known that a particular observer watching this sort of light emitting equipment, which this is the mirror, this is a mirror, and this is a mirror, where a light source come out from here and it actually goes to this distance, and as it travels in this distance and hit the second mirror below, it bounces back. So in this case, this distance here being covered is identified as the d distance, and the time that it travels back and forth is considered to as the change in time. Now to put that in equation, we can infer that the change of time is equals to, considering that this needs a back and forth to complete a full cycle, that is considered to be, that is why we need to count it as 2, because the first distance that is being measured is only the going of this photon towards this point, and thus and also counting that from this part where it bounces towards its original source. So that's why it's 2. 1, 2 bounces back. So we place here in 2 over the speed of light. Now what is this, the speed of light? It is the speed of these photon particles that is being emitted in here. The speed of light is equivalent to 3 times 10 to the power of 8 meter per second. So that is the speed of the photon particles, or the light particle. So this is actually the equation for our, this is a stationary setup. Well, on the second setup, which is the setup 2, we need to have 2 observers. The observer from a moving, we call this as an equipment of light beam. An observer in a light beam is traveling at a particular speed of, so we have an observer here, let's say this thing or the equipment itself is traveling, use of particular vehicles or spacecraft, or what kind of engines they use for it to be able to travel, for it to undergo displacement. So we have the first observer. This is the first observer, and we have the second observer, and the second observer. The first observer can actually, this first observer is observing this equipment of light light beam going back and forth, like this one, this observer, like how he does observe these things, this thing. So the light bounces and the light bounces back. The light directed to another mirror and bounces back to its source. While in the second observer, it has a different case, considering that this particular object is traveling at a particular velocity or speed. Now we can infer that if it travels around a particular distance, in the first place we have here, after 1 second it is right here, after 2 seconds, 2 seconds, and after 3 seconds it is already been moved in here. So for him, the movement of this photon light is normally like this, just like this. But in the case of the observer, to considering that he or she is outside this isolated thing, wherein this equipment is being carried by this particular vehicle that is in motion, that is considered to be less than the speed of light. As he observed that this equipment is moving, the light is also, the light that's being emitted from the source also move horizontally. After 2 seconds, we say this is just not totally the second, or we just make this as a reference of time, but this is not the standard or official thing that we use in measuring the speed of light, because the speed of light is very fast. It didn't actually pass through just a second. It really moves in a microsecond scales. So after it actually went into this far towards this point, it bounces back towards its source. So this leads us to the understanding that we can create a right triangle out of this illustration. You see, considering that this distance here towards this distance here is d, okay, this is d, this is a distance. Well, on this part, the horizontal part is the part where the particular vehicle, or the one that carries this equipment, has its own velocity, and this velocity is measured to meter per second. And also, what is the difference of time difference of this? We have the delta t over 2. So this is the equation for this part here. And on the second part, right, this one, the diagonal movement is denoted considering that this thing that moves in this line is the photon, and the photon is traveling at the speed of light, which is this one. So we can infer that this particles implies that this is v, speed of light is equals to the change of time over 2. Now we already have this particular setup being identified. Now we can move to the Pythagorean theorem. In the Pythagorean theorem, it is known that a squared plus b squared is equals to c squared. This is the very basic standard of the Pythagorean Theorem formula, which is also that is generally in trigonometry. Well, this is being visualized in a triangle, only for the right triangles. So we have here a right triangle. This is 90 degree. We have the opposite as the a square. We have the adjacent as the b square, and we have the hypotenuse as the c squared. Considering that in our illustration above here, we already have the right triangle and this right triangle, all these sides are being identified. These variables are already being identified. So let's see. This part here, the opposite part of the right triangle is denoted as d. We just have to copy this one. Is equals to d. We also need to square this one. While this part, the lower part, the adjacent part, is equals to this. The speed of the vehicle or the aircraft that carries this light equipment squared the change of time of this speed squared over 2 is equals to this part here, where there is an hypotenuse. So we have here the speed of light squared, change of time squared, and 2. All these 2's are being squared. And then now that we already plugged in our equation, it is now the time to derive this time dilation derivation. In deriving this particular formula, you need to only you only need to know the basics or the rules. So we have here, we need to first transpose this equation, this letter b, to letter c, towards the letter c. Then what will happen is looks like this: d squared. Considering that this is plus sign, whenever it is being transposed, it turns into a negative sign. This sign here is equals to, we just have to copy this one, c squared, change of time squared over 2 squared. So it is a plus sign. Whenever it is being moved, it turns into negative or minus. Still copy this one, v squared, the change of time squared over 2 squared. Now we have already the initial part of our derivation. Next is that the objective is to arrive at this time dilation equation. So basically we have here the d2. Considering that this is the same, all this delta time squared are the same, and it is a addition or subtraction equation, they should remain, the exponent should remain, and these variables are being combined. So it looks like this: change in time square is then change time square times, just have to copy this one without the time, the delta time. We have the c squared over 2 squared minus v squared over 2 square. So we have this initial and next derivation. To move on, now the other thing that we need to do is to keep that in mind, that this is our objective to find out. Now it is now the time to eliminate or reciprocate these two things. So what I do in this case is that what I do on the right side, on the right side, that's also the thing that I do here on the left side. So basically we'll be doing like, just have to place here, to rewrite our equation here above here, change in time squared, and we have the c squared 2 squared minus v squared 2 squared. We just need to have them because a whole number is already considered to have this over 1 below them. We just need to have a reciprocated copy of these two things to these two variables for them to get rid of them in every side. So what I mean is that this 1 over d square delta time square. So this is how it works. What I place here, I place it right here. So I also need to place it on the other side. 1 is equals to d squared change in time squared. So right at this moment we can now cancel the same part in a denominator and numerator. In canceling variables, this should be the denominator and the numerator that are the same. So we have here denominator of delta times square. You have to cancel that because it exists right here also. Delta times square exists. Have being cancelled, and also have this one. Cancel this one, d squared and d squared. So the thing that is left is this one. Change in time square is equals to, we only need to have this c square 2 square minus v square over 2 square. We have this 1 over d square. Now in this case that we have this transposed part and we already cancel this, cannot exist like 1 over delta times square. It cannot exist like that. It should exist as a whole variable. So the thing that would happen is that you just need to reciprocate this 1. Okay, so the reciprocation goes like this. You put this on the top and this 1 should be on the numerator. This a d square, it will look like something like this. So there is no need to really put the 1 below because it's already being implied. Well, on the other hand, on the other side, we have this 2 square over c squared minus 2 squared over v squared, and we also have this d squared. So this is the very basic thing. Now moving on, considering that we already have this particular equation, we can now simplify it more. The delta times square is equals to, considering that this 2 has the same value, and it uses sum and addition and subtraction, just have to copy this, and considering that we can already combine these two things, you can place 2d, and below we have the c square minus v square. And next is, we need to know, you can still simplify this into smaller one by means of, also get rid of this 2 if we have this 2 square d square over c square minus v square. To get rid of this, we need to put it in a square root. So basically this is being cancelled, this is being cancelled, the square root are being cancelled, and also in this one is already being cancelled. Based on the ruling, what you do on the right side should be also be done on the left side. That is why I place square root also on the delta t square to cancel the square. It's not cancelled because it's on the denominator though, numerator. So the thing that will happen is that it will come out something like this. The delta time is equals to 2d over c square minus v square. You really need to be critical in terms of understanding this because it's very hard to comprehend if you don't really know about it. Now the next is you have to put 2d in here, and you can factor it out. You can factor that out by placing it on the outside c and placing the square root. Considering that you already simplified it, something like this, there should be 1 in there, minus v square over c square. Now to fix everything, to fix all of our equation, you can see this 2d over c, and we have this 1 over the square root of 1 minus v square over c square. So if you remember this equation, it is this one. This is it, 2dc. So this is a stationary time that's being given here. So it only implies that this can be defined as change in time, or the delta time is equals to 2d over c. That's the thing that happens on the other paper. So this one is already delta time is equals to change in time. We have this 1 over the square root of 1 minus v square over c square. So there we go, we're running into the closer look of this equation, how we derive it. So basically you just need to place it up here, something like this. Change in time over the square root of 1 minus v2 and c2. So this is the final formula for our ST.